We're going to continue on chapter 14 and wrap it up. I hope we don't have too many more organic things to talk about. But last time we did talk some organicness. And again, we've been basically talking about esters here. And once again, esters have this as their functional group, the carbonyl carbon with the oxygen double bond there. Um, and our oxygen connected to a carbon. Remember, as we talked about, these guys are really made out of two other sort of organic groups coming together. We basically have, if you break it apart, kind of right there to the left there, where we do have the carbon oxygen double bond. Remember, that's from our carboxylic acid. And really going in the other direction away from the double bond is our alcohol. And again, we get that through that esterification reaction that we talked about. In the esterification reaction, we basically take those two groups and we basically add them together. And we basically are just going to take out water, some H2O. So out's going to go water. And then that is what's going to then allow us to connect those guys together to make that ester bond, which is basically there. R is a carbon group that's attached. Could be one carbon, two carbons, a bunch of carbons, however many carbons it may be. Um, we talked about some reactions that it makes, and it does, which is we talked about hydrolysis reactions that involves esters. And hydrolysis really means water's involved. And basically, our acid hydrolysis, it can be done as sort of an acid hydrolysis or a base hydrolysis. And in the acid hydrolysis, it is basically the reverse of the esterification reaction. You start with your ester, and basically through a acid and water, you will get back your carboxylic acid and your alcohol. Basically, you kind of recreated okay and perfect. Remember though, and again, that would be obviously our acid hydrolysis. If we did it in base, that's usually a strong base is involved, sometimes referred to as a saponification reaction, as we talked about, something like sodium hydroxide, potassium hydroxide. And in this particular case, remember, we really kind of do not get back both parts completed. Again, we will get the alcohol part back, but we will make, and we'll get back our, again, whoops, alcohol here. We'll get alcohol back, but we'll get a salt that will form. So again, two sort of hydrolysis reactions involving really water. And you can think of the acid one as sort of the direct reverse of making an ester. You could do that and you can basically break it back apart and get both components of it. With the base one, once again, you're not going to get back both pieces completed. You will get the alcohol back, but you will not get the again, the carboxylic acid back. You'll make more of that salt. And as we think we talked about last time, that's actually how you make soap. Just a really long chain of carbons on that. And you got sort of a soap type molecule that has a polar part and a non-polar part to it. We then talked about another sort of organic group, and that was amines. There it is. We talked about amines, and they are nitrogen containing groups. They're basically derivatives of ammonia. So they're very much ammonia-like. And with amines, as we talked about, we could have primary, secondary, and tertiary amines. And again, it kind of works the same way. We're talking really in that case, for example, how many carbons are attached to that nitrogen. And in this case, there is obviously one carbon attached, which would make it a primary. We can attach, say, two carbons to it. And that would be a secondary amine. And we could also attach three carbons to it. If I write 3 carbons, we'll go that way. There we go. And that would be a tertiary amine. As you can see, for every sort of extra sort of carbon group that we attach, we do end up with one less hydrogen. So again, I still think it's better just to count the carbons rather than the hydrogens. So again, and how many carbons are attached to that nitrogen give you primary, secondary, and tertiary. With the means, we decided, or at least I decided, I suppose, that we're going to take more of a common name sort of naming to it rather than the official IUPAC way of naming. And with common name with amines, we basically do it very similar to what we do with ethers. And we're just really naming all the groups that are there. So, if we had something like this, we would look at the nitrogen, and here we would have an ethyl group, and here we would have a methyl group, and we just sort of alphabetical order the groups there, and this would be something like ethyl, methyl, and this would be amine at the end. So for amines, we're just going to go kind of the common way of naming them. And again, you basically name as groups. Just like if you had two of the same groups, this would be dimethylamine here. This would be, by the way, trimethylamine there if you had 3 of them in that sort of tertiary type of situation. As I mentioned before, the hydrogens sort of deal on this one is a little bit difficult to remember. They do start with 2 hydrogens in the case of the amines, and it does have the 2 dots, which sometimes are not oftentimes drawn in on these pictures. So again, that's what gets it to the octet rule. So that's why, for example, over here, the nitrogen only has 2 hydrogens attached because that would be 4 electrons for the 2 hydrogens, 2 more electrons to the carbon bond, and those 2 non-bonding electrons on the nitrogen gives you the 8 total electrons that it needs for the octet rule. So again, sometimes in books like we use and stuff, they'll sometimes omit those 2 dots, and some people think they need like an extra hydrogen or something like that. But again, it doesn't because it does have those dots there. We also talked about our friend sort of an amine on a benzene ring, which is known as aniline. And that again, sort of that historical name. We also saw that, if we do have some groups that are attached, not necessarily to a carbon, but are attached here, we'll just do it that way. Attached here to the nitrogen. We do not use numbers. We do use an N to indicate that that group is attached to the nitrogen. So this would be N-methyl aniline. Again, aniline being this whole thing, our methyl group directly attached again to the nitrogen and not a carbon. So we do sort of reserve numbering for sort of carbons. And here, if you have some type of group attached to a nitrogen, we will use an N. Just like we use numbers, as we talked about last time, I think as well. If you have 2 things attached to that nitrogen, you would do like an N comma N. So just like you would kind of give the number twice if you had 2 things attached, you would do that as well here with the nitrogens. Any questions on that there? Okay. All right, so let's talk about some reactions that amines can undergo. Amines, because they are basically derivatives of ammonia, and ammonia is a weak base. Amines can also behave as like a weak base or a base. And in most cases, it's going to do the Bronsted-Lowry definition of an acid and a base. That would be our base. The water here would be our acid. We're going to send an H plus over, giving us NH4 plus and OH minus. Same thing down here. This methylamine would act as the base. Once again, water would act as the acid. And we're going to donate an H plus over. That is how we get NH3 here. And as we talked about when we were doing Bronsted-Lowry, Remember that it is not just a hydrogen, but you're also adding the plus or taking the plus away. So it does affect the charge. So that's how we go from something that is neutral to something that's a +1 charge because we added a +1 in there when we did the H, and we end up with our OH minus. So amines are basically a lot of weak bases are amines, these organic compounds, and they obviously could do our Bronsted-Lowry definition. Uh, what we do form as a result of that type of reaction is sometimes an amine salt, and those are sometimes responsible for some odors, as you see in things like fish, and sometimes are neutralized by acids. Why we squeeze maybe some lemons and over it. Amines again do our Bronsted-Lowry sort of acid-base reaction. Here we can neutralize it as well. If you react a strong acid with an amine, same thing is going to basically happen. We're going to send our H plus over. And again, we're going to gain it and we'll have our Cl minus there. And that's an amine salt. You don't have to name the salt or anything like that, but basically we'll make a salt here. It's kind of like an acid-base reaction, but we kind of don't get water in this case. We just end up with like a salt that occurs. Now, properties of ammonium salts, they're usually convert ammonium salts before they're used in drugs. Ammonium salts are solids at room temperature. They're odorless. They are soluble in water. So remember, one of the other sort of aspects of an amine is because that is a hydrogen that is directly attached to a nitrogen, it can participate in hydrogen bonding, right? So remember, again, to participate in hydrogen bonding, you need a hydrogen that is directly attached to either a nitrogen, oxygen, or a fluorine. So that means here we have hydrogens that are attached directly to them. Definitely for primary and secondary amines, which has 2 hydrogens and 1 hydrogen. Remember that tertiary amines do not have a hydrogen attached there. So they cannot sort of hydrogen bond themselves, if you will, but they can still participate in hydrogen bonding because a hydrogen from something else can bond to the nitrogen and do that hydrogen bonding as well. So the tertiary rise can still kind of do that. Ammonium salts are active ingredients in a lot of medication, like Sudafed, Benadryl, and again, you can see some of these ammonium amine salts over here sort of happening. Also in cocaine as well. Here's our amine happening over there, and our amine sort of group as well. Alkaloids are amines in plants. They're physiological active compounds. Something like nicotine here is a stimulant. And again, we have our amine sort of happening over here in nicotine. Caffeine as well. So again, we have our amine sort of groups happening there. Our nitrogens attached as well. And morphine and codeine as well, as you can see the Okay, let's take a look. So we see amine just tells us our nitrogen containing group. Since we were kind of doing the common, take a similar approach to drawing it like we do with our ethers. So since I know there's definitely a nitrogen and we're gonna have some carbon groups attached to it, I would probably start with the nitrogen in the middle. And then at when we just need to attach our group. So propyl is a 3 carbon group. And again, you can put it really on either side of the nitrogen. It's your call, whichever way you want to go. I'm going to go this way, and we'll put our 3. And then methyl is a 1 carbon group, which will obviously go on the other side. And in this particular case, will look like this. But one of the things we do got to remember is the nitrogen also may have a hydrogen as well. So just want to kind of remember octet rule. So we do see 2 electrons there, 2 electrons there. once again, although sometimes never drawn, we do have those two electrons there. So that's 6, which means this guy really should have a hydrogen hanging off of it as well, again, to kind of complete it. If you're going to do line structure, I would do the same approach. Start with the nitrogen, do your kind of 1, 2, 3, and your 1. And in this case, obviously, you would probably draw in your hydrogen in this case as well to show it. Any questions on either of those? Yeah. Are you talking about like yeah, you could put those groups on either side. It's fine in that as long as obviously they can't be on the same side and stuff, but as long as they're on opposite sides, it's all good. Yeah. Other questions? All right. Aniline, what and here, this definitely would be carbon number 1 where that group is attached. And by the way, you also, in this case, could attach that group on any of the carbons on that chain, wherever you want to attach it. That would be carbon number 1, obviously, wherever you did that. So for me, I could go right or left. And again, we have that option as well because that is really benzene, which means it does have 3 double bonds. So no matter which way you go, you're always going to go through a bond, a double bond, and it also has a resonance structure as well. So I'm just going to go to the right here and put my chlorine. And by the way, again, I do know in this case that we will have 2 hydrogens because if we just kind of count our bonds, there's 4. So we'll need those 2 hydrogens to make the octet rule for it. And that's how we know the nitrogen up there should have 2 hydrogens. Also, because that is a primary amines, which will have 2 hydrogens because of that. Any questions on those there? All right. Here I say the last organicness of the season here is the amides or amides, whichever way you like to call them. And they have a functional group of carbon oxygen double bond to actually a nitrogen here. And it is really a combination of a carboxylic acid and an amine. Yeah. So it's our carboxylic acid and amine coming together here to make this bond. And as you can see there, we see that our amide bond. This bond as well, you'll see in a later chapter, is a peptide bond that amino acids use to bond to one another. So that is the amide bond here, how they come together. So amides are derivatives of carboxylic acids, as I mentioned, and really ammonia. And maybe not surprising at this point, we're probably just going to take out water to do that. And we're going to take out 2 hydrogens and an oxygen. And that's going to leave us, again, if you just kind of think about these guys here, and you got maybe something like this. Whoops, come here. H. And maybe a carbon or something. So we take out some water there. And once again, if you just kind of get rid of that water part, now you have your amide bond there, our carbon oxygen double bond, and our nitrogen coming together. So kind of similar to our ester bond, how it comes together. But instead of attaching it to an alcohol here, we're going to attach it to create that bond right there. That is also obviously where they would break apart and also where they come together here. And it is sort of water sort of coming out to allow them to sort of come together. So preparation of an amide, once again, is basically just put those 2 things together, take out the water, and you will end up with what you need. And much like anything, if you're going to kind of draw these guys, I would kind of draw them like we see here, where you can kind of visualize the amide or the water coming out. And really at that point, kind of like the ester, all you have to do is just squish everybody together and connect them through that point, and you'll end up with your bond there. So here we take our propanoic acid and our ammonia, take the water out, and we make our amide bond here, which is right there. And here we have methylamine, which once again is an amine, taking out our water. And basically putting the two boxes together will get us our amide bond. So like I said, it's an important bond. It's the bond we see as a peptide bond in amino acids, and pretty much all amino acids have kind of those two groups on, and they have sort of a carboxylic acid group, and they also have like an amine sort of group, an ammonia sort of group, and that's how they bond. All right, so why don't you draw the outcome of this reaction here if you put these two guys together? Okay, so let's take a look. And again, I would recommend maybe just kind of drawing these guys sort of facing each other. And again, it may help you just kind of visualize what you need to do. So we want kind of both functional groups kind of facing one another. And if I did that, just kind of turn it around. At this point, hopefully, we're going to take water out. So however you want to kind of arrange that, you can just put a box around it. And once again, that's going to kind of be where the water is going to come from. And when you do that, obviously you'll get water. And really nothing else is going to change other than we're just going to kind of squeeze everybody together at the correct spot there. So this will look exactly the same. We will still have our double bonded carbon to the oxygen there. No, that's not right. No, it should look the same. Probably should draw it the same. Let's try that again there. Go. So we'll have our single bonded carbon to our double bonded carbon. There it is. And once again, we're obviously going to get rid of the water part here in the box. So we're going to connect this, making our amide bond, which is right there. So our carbon, oxygen, double bond to our nitrogen. And really the only thing left is that right there on the other side. And we will end up with something that looks like this. So once again, nothing weird happens. We're just going to basically take water out and push them together. That is always a connection point between those two guys. Carbon, oxygen, double bond to the nitrogen. That is always where they come together and make that bond. Any questions on that there? Go. All right, naming amides. Nobody cares. All right, so we're not going to name them, so don't worry about it. All right, still not naming, still not naming, still not naming. Still not naming. Urea here is an amide, and again, you can see our amide bond right there on either side, actually. Barbiturates as well are also amides, and again, you can kind of see the amide bond right there, a connection. Aspirin as well has an amide bond on it right there. Now, the one thing we're going to talk about amides, so you're not responsible for drawing them, you're not responsible for naming them. You obviously need to know the functional group of them. And you need to know these two sort of reactions as well, and also how they're made, obviously, between a carboxylic acid and an amine. It also, much like amines, will go through two types of hydrolysis. It will go through an acid hydrolysis, and it will go through a base hydrolysis. And kind of opposite of amines here, it's actually the base one that kind of gets you both parts back. Here in the acid hydrolysis, we will end up with a carboxylic acid and an ammonium salt. So we'll just kind of look at that there. So if we take a look at it, here is our amide, and obviously where they come together is essentially where we're going to break it apart. So if you had to, that is really where you want to start. You just want to break it back into its kind of parts, which will look something like this. And we basically have this part here as well. So in this particular case, we have sort of a carboxylic acid part, and we have an amine part, or something that comes from ammonia in this case. And in this case, we are going to add back and always get the carboxylic acid here. So a good way to remember that is acid hydrolysis. I get the acid back, right? So carboxylic acid is the one that I get back in this case. And however you want to kind of think about it, for our purposes, is not super important where everybody comes from. But we're going to take an OH here and sort of complete our carboxylic acid from there. If you just kind of keep track of some of the other things, we have a hydrogen there, also have a hydrogen there. So that is going to come back out over here to get our ammonium salt, and that's going to make NH4 plus. And there's just Cl hanging out there, which would be just Cl minus. And that's a salt, so that's a positive, negative guy. That's an ionic compound. That's ammonium chloride is basically what that is. And that is what you get in the acid hydrolysis. You basically get the carboxylic acid back, and you get this sort of ammonium salt back along the way here. So you don't really get the completed amine back. Now, in the base hydrolysis, same idea. We're going to break it apart right here between the connection. But here we are using a strong base. And in this particular case, we are going to get the base part of it back, which is the amine. So we will sort of complete the amine. And you could kind of do similar type of idea. You could kind of draw the two parts where you break it apart. And obviously over here we have this guy, which is definitely more of an amine. And like I said before, we are going to get our amine back. So we're going to borrow a hydrogen here, and that's going to complete our amine. So you can think about it. And if you think about sodium hydroxide, once you borrow that hydrogen, you're left really with a negative oxygen and a positive sodium in this case. And that is what's going to come over here. We're going to make a carboxylic acid salt over here, and we will get that back. So for the amide, you could kind of remember what you get by what hydrolysis you're doing. If you do the acid hydrolysis, you get the carboxylic acid back. If you do the base hydrolysis, you get the amine back, which is essentially a weak base. So you kind of get the base back when you do that one completed along the way. Any questions on either of those two reactions there? And if I, there we go. So if we take a look at this one here, since we not talking about names, so we'll just take a look at one more example here. This once again is the base hydrolysis. So as I mentioned before, we're going to break this guy right there. That's going to give us our two parts. If I count up how many carbons I got there, one more, I think. There we go. And the other part is going to be the other side of it. I'll just go below it here. And again, in this case, I'm doing the base hydrolysis, which means I get not the acid back, but I get the base back completed. That's going to borrow a hydrogen. Again, you could kind of get rid of the hydrogen if you want. And the oxygen is going to end up over here. Again, not as a completed carboxylic acid, but once again, as a salt that's going to happen here. So on this one, acid gets you the acid back completed. Base hydrolysis only gets you the base guy back, and the other one, the opposite guys end up as salts, basically, because you're out of elements, if you want to kind of think about it that way. Any questions on that there? Since we don't care about names of these guys, we're not going to name them or draw them. And now we're done with organic. That felt good. All right. There's organic out the window. Any questions on that there? All right. Why don't we go off to our next chapter? Because why not? All right, so we're gonna try to find what I want to hit. There you go. All right, so we're gonna change gears a little bit, and we're gonna go back to chapter 13, which is carbohydrates. So we're on the back end here, the final three. Well, carbohydrates, some bread, some protein, some meat, and I'll do some fats and lipids to finish it out there. All right, so we're going to talk about carbohydrates here. And those are hands and chiral molecules. So when we talk about chiral molecules, a chiral molecule is a molecule that basically, excuse me, has a mirror image that is non-superimposable. And that's why we have the hands. So if you put this hand up in the mirror, you get the other hand staring back at you, basically. And if you take the hand from the mirror out, you could take and do whatever you want to that hand. You could rotate it as much as you want. It will never fit on top of the other hand perfectly. You could get thumbs to match, but we got palm up, palm down, so that's not good. You could go palm down, but now thumbs are on the wrong side. So you could rotate that as much as you want. Don't hurt yourself doing it. But you will never be able to do any type of rotation that will allow the mirror image to basically come out and superimpose on the original image. And that is what a chiral compound is. Usually a chiral compound will have at least one, what is referred to as a chiral carbon. A chiral carbon is a carbon that has four different groups attached to it. So when you look at a carbon, if there are four different things attached to it, then that is a chiral compound, and most likely will be a chiral compound and have a mirror image that will not superimpose on one another. So if we take a look here, we look at this carbon right here in the middle. It has a hydrogen, which is different than a chlorine. That's different than an iodine, and that's definitely different than a bromine. So that is four different groups attached, which would make this carbon here a chiral carbon. And if I put that up to a mirror, this would be what would be reflecting back in the mirror is this image. And if I take that image out and I rotate it as much as I want, although it may be hard to visually see it, there will always be something that will not match. So there will always be a group that is just not the same group, even though you may just think, can't they just keep rotating? And we'll do that. Remember that these things, for example, here is a tetrahedral sort of arrangement. So they have different bond angles, right? So as you move one molecule may be coming out and the other one may be going backwards, and they will not sit perfectly on top of each other. So there will always be something that won't match. So as you can see here, although we could get kind of two of the four things to match, the other two guys are not going to be the same groups on top of each other when we take the mirror image and the original guy. And that's different than an achiral compound. An achiral compound is a compound where the mirror image will superimpose on one another. And it also means that if you look at, for example, a carbon, it does not have four different groups attached. So it has at least two groups that are the same. So if we take a look at this guy here, this carbon in the middle is an achiral carbon because there are two bromines attached to it. And because there are two bromines attached, you can take the mirror image, which is this guy, and you can successfully just rotate it around and it will fit perfectly on top of the original molecule in this case. And that makes it achiral. So when we talk about carbohydrates, sometimes we talk about a chiral carbon, which has four different groups attached. Sometimes we talk about an achiral carbon, which does not have four different groups attached. And just so you know, it can in some carbohydrates have multiple chiral carbons in there as well. Here are some chiral and achiral things. So we got gloves, which are chiral. We got an achiral soccer ball. Right-handed scissors are chiral. We got an achiral glass. It has a plane of symmetry down the middle. You split that in half, basically have both things on the same side as well. Okay, let's take a look. We'll start here. We'll start with the carbon. It's a good place to start. And attach that carbon. That's a methyl group, which is different than an ethyl group. And both of those are different than a chlorine. And those three are different than a hydrogen in this case. So that is definitely four different groups attached to that carbon. And that would make this a chiral compound. That means that if you put that up to a mirror, its image in the mirror will not superimpose on itself. If we take a look at this carbon, that is a methyl, which is different than a chlorine. Chlorine and methyl are different than a hydrogen, but that's a little problematic. We actually have two of the same groups in this case, and that would make this an achiral compound. And that means if you put that in a mirror, its image should be able to superimpose on the original structure. Lastly, here, if we take a look at this carbon, one group that's different than this one, those two are different than this one, those three are different than that one there, and that gives us four different groups that are attached, and that would be a chiral compound, which once again, its mirror image would not superimpose. Any questions on that one there? And in this case, we're sort of counting groups. We do kind of look at the hydrogen as a group sort of that's attached. We normally don't kind of think of hydrogen like that. All right. Now, Fisher projections are two-dimensional representation of a three-dimensional molecule. We usually place the most oxidized group towards the top. We use vertical lines in place of dashes and for bonds that go backwards. And we use horizontal lines in place of wedges that come forward. So sometimes, especially in organic chemistry, I could draw a wedge here. Sometimes people will use a wedge in their pictures to indicate that that group is kind of like coming out of the paper. And sometimes people will use like a dash line to indicate whatever is attached there is going like behind the paper in sort of three dimensions. So Fisher projections will use the sort of vertical lines and also horizontal lines in place of those sort of situations here. And again, that's what we see here. We also will oftentimes see a chiral carbon as just an intersection of two lines. So a lot of times you'll see a carbon or a chirocarbon as that intersection between these two lines. So carbon, carbon, carbons are there, even though sometimes they may not be sort of written in as carbons. So almost like a line structure with carbohydrates, you see those crossing of lines. That's usually where you'll find your carbons attached. Now, we also, for carbohydrates, will sometimes use D or L notations. And D and L basically, for the most part, stand for left or right, if you will. And D stands for right, and L stands for left. That one seems easy to remember. L for left, right? And D for right. And what are we talking about, sort of left or right? Well, we're talking about in terms of carbohydrates, the location of the OH group on the very last chirocarbon on the carbohydrate, the one furthest away from the top, basically. So the very last, not just carbon, but the last chirocarbon, and which side that OH group is located on. And here we can see this is usually the group or a similar group towards the top. This right here would be our very last chirocarbon, and we do see the OH here on the left, so this will be L-glyceroldehyde. Now, you may be asking, what about the carbon at the very bottom? So if we take a look at the carbon at the very bottom, it looks something like this, if you will. So it is attached to whatever is above it, which is different than the OH. But in this particular case, it does have two hydrogens, which means that that carbon on the bottom is achiral, right? So that's an achiral carbon. And I would say not 100% of the time, but fairly close. If you go to where that CH2OH is in a carbohydrate and can just kind of bounce up one carbon from it, that's a lot of times your last chirocarbon that you will have to use to sort of decide DNL. Once again, not 100% of the time, but pretty darn close. That's going to be kind of where you would want to look from this guy. So these are very common, as we will see. You will kind of have this kind of functional group at the top. We usually will have this CH2OH on the bottom. And again, if you just kind of go one back from that guy, a lot of times that is where you're going to kind of find your chirocarbon or your last chirocarbon. Once again, you can have multiple chirocarbons in a carbohydrate, but that's sort of where you'll usually find that last one to help get the D or the L. All right, so take a moment here and decide, is each of these mirror images? So imagine a mirror, I guess, right there. And can the double negative, I think, on this sentence, indicate whether each mirror image that cannot. Okay, so how would I want to kind of solve this? Probably just go by our definitions of what we've been talking about, which is chiral and achiral. And obviously, the chiral compound has a non-superimposable mirror image, and obviously, a achiral has a superimposable image, mirror image. And what the difference between that is, again, if something is chiral, when you look at the carbon, we should have four different groups attached. So if we take a look at this guy, that is different than this guy, that is different than this guy, that is four different groups attached. That's going to be a chiral compound, which means we should have some non-superimposable mirror images. If we take a look at the bottom one, that is different than that, which is different than that. But here is a problem in terms of chirality. We got two of the same groups there, two hydrogens, which means that this guy is going to be achiral, which means we will have a superimposable mirror image. Any questions on that there? So the answer, the double negative there. The first one is yes, it cannot be superimposed, and the second one is no, it can be superimposed, right? Okay, we're going to continue on here. So we're talking about obviously carbohydrates. Let's talk a little bit more about carbohydrates. Carbohydrates obviously is a major source of energy from our diet. They are composed of carbon, hydrogen, and oxygen. They are called saccharides, which means sugars. We use it for energy, right? Goes through a little glycolysis and use it to sort of power everything. We also store some of it away for gluconeogenesis in case we need to break it back down for some stored energy. Carbohydrates are produced through photosynthesis in plants, such as glucose is synthesized from CO2 and water, energy through cellular respiration. Again, we have this sort of like carbohydrates and cycle that goes around water and CO2 through photosynthesis. Let's talk a little about some different types of carbohydrates. There are monosaccharides. Monosaccharides are simple sugars. They are simple carbohydrates. Mono means one, so they come as ones. We have disaccharides, which is basically a combination of two carbohydrates together. As we'll talk about, pretty much to do that, you take water out. So we take water out from the two carbohydrates, and that kind of sticks them together, and that gives you your disaccharides. We're going to talk about a few specific disaccharides in this chapter that you'll have to sort of know what monosaccharide it comes from. Then we have polysaccharides, and polysaccharides are really just a big old chain of a lot of sugar molecules together. They're each put together by removing water from two carbohydrates, and then they will bond together. So as you can see here, if you wanted to sort of break disaccharides apart or polysaccharides apart, you would actually just put the water back in, and that would break them apart. Just like that's how we make those two things, by taking the water out. So let's start with monosaccharides. Monosaccharides consist of 3 to 6 carbon atoms typically. They have that carbonyl group that we saw in organic chemistry, and a reminder, that is our carbon oxygen group there. That's our carbonyl carbon. And a reminder that that is, again, as we talked about there in the organic chapters, it is a polar sort of group there. Again, the carbon being more positive, the oxygen being more negative. It also contains, for the most part, one of two organic functional groups that we saw. Usually a carbohydrate will either have a aldehyde group, and a reminder that our aldehyde group is this group right here, our carbon oxygen double bonded to a hydrogen. So some carbohydrates will have the same exact aldehyde group that we see in organic chemistry, and some will have the ketone group. And it also is the same group that we saw in organic chemistry. That will be our three carbon group with the carbonyl carbon in the middle. So we will see a lot of those or some of those organic groups pop up here in carbohydrates. And again, these monosaccharides will either have up on top, it will have our aldehyde group or our ketone group. Now, just like in organic chemistry, the location of these groups are also similar. And in organic chemistry, as we talked about, because our aldehyde group has that hydrogen, it will also find its way in a carbohydrate to be at the very end. And in this case, at the very top of the carbohydrate is typically where you would put the aldehyde group. It cannot be in the middle, again, because of the normal rule of hydrogen will have too many bonds. So it has to be at one end. In the carbohydrates, we put it sort of at the top. It's the most oxidized group there. That is the group, if you remember right, could go through oxidation and become a carboxylic acid, right? So it could go through that oxidation reaction and do so. Also, like in organic chemistry here, we will not find the ketone group there, or at least the carbonyl carbon of the ketone group, which is our carbon oxygen double bond. We will not find that at the end because it's got to at least be one in, because you have to have three carbons in a row with the middle carbon having that double bonded oxygen. So we'll never find that carbonyl carbon at the end. So we'll have an aldehyde group that will be at the end, and again, typically at the top. We will have a ketone group, which will also be at the top. But again, the carbonyl of the ketone group will not be at the very end of the carbohydrates. They also will have several hydroxyl groups. Hydroxyl groups are OH groups, so they'll have a bunch of these OH groups that are attached as well. So one classification of monosaccharides is based on what sort of organic functional group it has. So this one here has our aldehyde group. And here we will call a carbohydrate that has an aldehyde group on it. It will be known as an aldose. So it kind of sounds like aldehyde, aldose, aldehyde. So if you have the aldehyde group on it, it's going to be an aldose. We also will classify monosaccharides based on how many carbons they have. So if they have 3 carbons, 4 carbons, 5 carbons, or 6 carbons, 3 carbons would be a triose, like tri for 3, tetra or tetros there for 4, penta or pentos really for 5, hexos from like hexa, like we talked about with those prefixes, for 6 carbons. Because the sort of organic group is always at the top, this is always, in terms of numbering, number 1 carbon there. So as close as you could get to that functional group. And in the carbohydrates, you can think of it that way as well. The sort of organic functional group kind of takes the priority in terms of numbering. We want to give it the lowest. It should also be usually at the very top of those drawings. This would be carbon number 2. This would be carbon number 3. And this would be carbon number 4. And this would be a tetros, as it has 4 carbons, and this is an aldose tetros. We are not going to really name per se this monosaccharide, this particular one, but that is how it is arranged. It is also sometimes abbreviated, as you can see there, as an aldotetros, which again means it's an aldehyde group and it has 4 carbons attached. Take a moment here on this particular guy and decide how. Okay, let's take a look and see. We'll start with carbon number 1. Is carbon number 1 a chirocarbon? It is not. It actually only has 3 things attached. It has That, and then everything underneath it basically is only three. So it doesn't definitely have four things attached. How about our friend number two? Is that a chirocarbon? That is a chirocarbon. It has four different things attached. It has all that above it. It has this guy, it has this guy, and it has all that below it. So those are all four different things that are attached, and that would make that a chirocarbon. Now, if we go to we'll go to number three there that I just erased. Number three a chirocarbon. Number three is also a chirocarbon. And again, if we look at number three, it has this group, that group. It has that group, which is different, and it has everything above it, which is different as well. So that is the four different groups here. That would make number four a chirocarbon. Number four is not a chirocarbon as it has obviously two hydrogens there, and that's going to prevent it from being chiral. First off, any questions on that there? Say again? Yeah, it is not chiral. It's achiral, and that's because it has these two hydrogens here. So it has these two hydrogens that are attached to that carbon. So if you drew it out, it basically has, in addition to everything else, it has these two that are the same group and it doesn't have four different groups attached. So typically speaking, when you see that CH2OH, like I said before, that's going to definitely be probably achiral. And usually that's the case that happens there. By the way, this would be DRL, this one. It would be D as we're looking for our very last chirocarbon away from our functional group, basically. And the OH there is on the right there. So have a little D action there. Yeah. Any questions on any of that stuff there? Now, we can also have, as I mentioned before, a monosaccharide that basically has the ketone group attached, and that's what we see here. And right here is our ketone group. That is a carbon, 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 three carbons in a row with a carbon-oxygen double bond. So that's your ketone group, basically. And kind of like our aldose, we call this for our monosaccharides a ketose and that basically has a ketone group attached to it. And as we just talked about in a second ago, unlike our aldehyde group, which we'll see that carbonyl carbon up there on top, here we're going to actually see it at carbon number 2 is where our carbon oxygen double bond is at. And this would be 3, 4, 5, and 6. So just like the other one, we could also classify this based on the number of carbons. This one here has 6 carbons, which means this would be a hexose. So this would be a ketose hexose or a keto hexose. This is fructose, which is something that you should be able to put a little star next to. We'll see it a little bit later on as well. But you need to be able to recognize that structure, I think, for the final exam. Yeah. So we'll talk about some things for the final that you maybe need to know as we go through these last 3 chapters. So, and I think we'll see another picture of it in just a bit here. This particular one has how many chirocarbons? It does have 3. Once again, this guy up on top is not going to be chiral because he's got the same 2 hydrogens. And with this ketose group, as you can see, you got this CH2OH on top and on bottom. This is not going to be because it doesn't have 4 groups attached. This one right here would be chiral as it does have 4 different groups attached. This one down here also would be chiral as it has 4 different groups attached. And this one right here would be chiral as well because it has 4 different groups. So carbon 3, carbon 4, and carbon 5 should be chiral carbons in this case. And that would also make this guy a D as well as our OH group here on our very last chirocarbon is hanging out over there on the right-hand side. Any questions on that one there? So if it has a ketone group, then we call it a ketose. And again, triose, tetrose, pentose, or hexose, depending on the number of carbons. Questions on that there? All right. So for each of these, identify them as an aldo or a keto, also tetros, pentos, hexos. And while we're at it, why don't you also identify it as either D or L and the number of chiral carbons that you see. All right, so take a moment for each of those, see what you come up with. Okay, let's take a look. We'll start with the first one. We'll start with is it aldo or keto? This one is an aldo as we have the aldehyde group here. So that's going to be an aldo. In terms of carbons, this again would be carbon number one, where that group is at. Two, three, four, five, and six, numbering downward. So that is six carbons, means it's a hexose because it has six carbons. What else are we looking? Number of chirocarbons. How many is it at? It does have four. This number two should be chiral. Number three, number four, and number five here should be chiral. Again, the very top one is not. There's not four different groups attached. The very bottom one, once again, has those two hydrogens, which makes it achiral in this case. And so four chiral carbons. And here we're going to go very last chirocarbon from the group up on top. And we look at where our OH is hanging out, and we're going to get a D in this case. Yeah. Any questions on any of those there? Take a look on the right. This is a keto, right? We got our ketone group. Once again, that is three carbons in a row that has a carbon-oxygen double bond in the center carbon. So that is our ketone group, just like in organic chemistry. That would make this a keto. We would number to give that carbon oxygen double bond the smallest, which means it will end up at carbon number two there, three, four, and five. So this one has only five carbons, and that would make it a pentose. And in terms of chirocarbons, here we are shooting with only two. These two right here, number three and number four. Once again, the guy at the very top has the two hydrogens, just like the guy at the very bottom. Double bonded carbon obviously doesn't have four different groups attached. So that would give us two chiral carbons. And once again, look at the very last chiral carbon down the road there. Our OH group there is on the right, which technically I guess would be a D. Any questions on any of that there? All right, so let's talk a little bit about some of the structures of some of these monosaccharides. As we've been talking about, we can use Fisher projections. We do, again, place the most oxidized group up on top. Essentially, that's your organic functional group. It's going to go to the top. We show the chirocarbons as intersections. And again, wherever you see an intersection, as we talked about previously, that should be a carbon. So almost like line structure with carbohydrates. Sometimes we, don't put the carbon in there, and where that intersection happens, once again, is our carbon. And again, here we do see our D and L notation for left or right here. So these are some D and L monosaccharides. So we have glucose, ribose, and galactose. Just put a little star on this page. You need to be able to perhaps recognize those structures, not necessarily draw them, but be able to recognize them as glucose, ribose, and galactose. Yeah. So here again, we have our aldo, and we got one carbon, two carbons, three carbons, four carbons, five carbons, and six carbons. So that would be a hexose coming down. This would also be D because, again, this is our last chiral carbon. And that OH group is on the right. By the way, this guy's got one, two, three, and four chirocarbons. All of those are going to be chiral as they have four different groups attached. Over here for ribose, also an aldose, has one carbon, two carbons, three carbons, four carbons, and five carbons. It would be a pentose in this case. And it has three chirocarbons, chiral, chiral, and chiral. And here at our last chirocarbon down the road there, our OH group again is to the right, which would make it D. Lastly, here we see again an aldo group here with one, two, three, four, five, and six carbons happening. So this also is a hexose. And in terms of chirocarbons, we got one, two, three, and four. In this case, our very last chirocarbon has the OH group on the left-hand side, and that would be L. So again, in determining D and L, we're looking for the very last chirocarbon from basically the top functional group. The very last one down the road there is where we're looking for. And again, on whichever side there that OH group ends up being on that chirocarbon is the one that we're looking for. And like I said, you can almost autopilot it, but not 100% of the time, but almost just go one back from the bottom and you'll usually probably be in good shape most of the time. All right, so take a moment here and decide L or D for each of these. And why don't you also identify how many chirocarbons each one has? Okay, so let's take a look. Starting with A, this right here should be a chirocarbon. That right there, and that right there. So those three should be chiral. And obviously, this is going to be our very last chirocarbon from the top, and our OH is on the left there. So that should be an L in this case. Once again, over here, that should be a chirocarbon. That should be a chirocarbon. And I think that is it in terms of chirocarbons. And again, our OH group here is on the left, so it should be L. And once again, here we have a chirocarbon there, there, and there. And our last OH group there is going to be on the right there. Any questions on that there? Okay. All right, so let's talk a little bit about some of these. So as I mentioned before, this is glucose, which you do need to, again, perhaps be able to identify the structure if you see it. It is known as obviously blood sugar in the body. It's the monosaccharide in polymers such as starch, cellulose, and glycogen, as we'll talk about. Um, We oftentimes will measure our blood glucose level, and if we're normal, obviously we're in the normal range. If we're hyperglycemic, again, hyper means more than sort of normal blood glucose. And if you're hypo, obviously hypo means less than. And sometimes they'll test obviously your glucose levels. They'll ask you when you take a blood test, right? Did you eat or not eat, right? So anything before it, as it can make a big difference if you take the cookie right before you take your blood test, right? You go, yeah, I had to eat my cookie. Fructose, you also, again, do need to know the structure of fructose, so maybe put a star next to it for the final. Again, it's a ketohexose. It is found in fruit and honey. In the body, it will convert into glucose. And galactose as well, which I think was the other one on that sort of chart that we looked at. Galactose, very similar to glucose. It's obtained from lactose, which is a disaccharide. It is similar to glucose, except for on carbon number 4. which would be here, 1, 2, 3, and 4. So here's our difference there between the two is on that carbon right there. Again, that's going to be D as our last carbon. We have our OH over there on the right-hand side. You're not going to have to worry about drawing, so we won't worry about it really. But you do need to be able to recognize it. So let's talk a little about the cyclic structure of monosaccharides. So monosaccharides can be sort of in a straight chain if you want to kind of think about it that way. They can also kind of wrap themselves up and kind of close up and make a cyclic structure, kind of similar to some of the cycloalkanes that we saw there in organic chemistry. And for the most part, they will make one of two types of sort of cyclic structures. One that looks like cyclohexane, but is missing a carbon, and one that looks like cyclopentane, which is also missing a carbon. So this looks like our cyclohexane. But unlike cyclohexane, which actually has 6 carbons, this guy only has 1, 2, 3, 4, and 5 carbons. So it is a 5 carbon member, bless you, ring. Again, where that kind of 6 carbon is where that comes together, the both ends, and it incorporates actually an oxygen into the ring rather than a carbon. And this guy over here on the right looks again very much like our cyclopentane, which obviously has 5 carbons. But this guy, once again, because it also has an oxygen that really does end up in the ring when it sort of closes in on itself, it's actually a 4 carbon type of structure that ends up being there. So we will either kind of have a 5 carbon ring or a 4 carbon ring. And we're going to talk about how to kind of turn it from kind of the straight structure into the cyclic structure here. And basically, it does form when a hydroxyl group on carbon number 5 reacts with the aldehyde group or the ketone group, especially if you have a hexose or 5 or 6 carbons. We always sort of it always sort of attacks at the carbon oxygen double bond. So that's sort of where it comes together and kind of closes up in a ring type structure. So what happens is it will form a stable cyclic hemiacetal. If you remember, we talked about hemiacetals. Hemiacetals have a carbon group that's attached to a hydrogen, attached to an oxygen carbon group, and also has an OH group attached to it. So that is a hemiacetal. That is what you get when you take like an aldehyde and add 1 alcohol to it. You get that hemiacetal that we talked about in those reactions. So we formed a stable hemiacetal when the carbon oxygen double bond and the OH are part of the same molecule. For hexoses, the hydroxyl group at carbon number 5 will react with the aldehyde and our ketone group. If it's not a hexose, then it's usually the last chiral carbon down the chain is sort of what comes in and sort of closes up the ring. The cyclic structure of the diisomer has the last CH2OH located above the ring. So for the most part, this is the arrangement wherever the oxygen is in the ring, or if you have this ring, that CH2OH, that is the last CH2OH, at the very bottom. So that is where that guy will sort of always end up on the ring, kind of to the left of the oxygen, and then the rest of them get put on accordingly. So let's talk a little about sort of how to do that. And let's just say we took something just like a made up one here. We'll just do this here. Yeah. And we'll just kind of do some things here. Okay, so let's just say here that we have this hexose and this aldose, which is a hexose, and we want to kind of turn it into a cyclic structure. So how this basically works is a good way to do it is to obviously number our carbons so we could kind of keep track of where everybody's going to end up. So remember, the sort of organic guy is going to end up with the obviously lowest number should be up on top, the functional group. That's going to be 2, 3, 4, 5, and 6. So one approach is you could just take this structure and basically just drop it on its side. So just take it and just tip it over to its side. And if you did that, it would look something like this. If you just kind of dropped it on its side, and I'll just kind of go, just do CH2OH here at the end. And I'm going to count this the same way. So that'll be carbon number 1, that'll be carbon number 2, that would be carbon number 3, carbon number 4, carbon number 5, and this would be my carbon number 6. And once again, if I just took it and just let it drop to its side, everybody on the right-hand side, right, would eventually just kind of drop to the bottom, right? It would be on the bottom, and they would go to the bottom. And everybody on the left-hand side here would go to the top, right? So again, if I just dropped it like that, those guys are going to go to the top. So that's how I'm going to kind of know where everybody's going to go here. So if I did that, I would have an OH on here, I have an H, I would have an OH and an OH, and then obviously here I would have an H, an H, an OH, and an H. So again, all I essentially did is just took the thing and plopped it on the side. And that's what it's going to look like. So in this case, when we have really a hexose, it will be carbon number 5, which is really our last chirocarbon down the road here. This is basically our very last chirocarbon. And that's going to basically go and attack wherever that carbon-oxygen double bond is. And those guys are going to come together to make that ring. And it's going to be one of those two rings we just talked about. This is also a really good way to do it to figure out which ring you should draw. So if I put them together here and I just count the carbons that are part of the ring, that is 1 carbon, that is 2 carbons, that is 3 carbons, that is 4 carbons, and that is 5 carbons that's going to end up in a ring. So now I know the ring that I need to draw is the 5 carbon ring. And remember, the 5 carbon ring is the one that looks like cyclohexane, but once again, missing a carbon. It has the oxygen in there. And what I also know in this case is to the left of that oxygen is where I should end up with my CH2OH group that is at the bottom. And because that is the group that's at the bottom, I know the carbon number for that group is carbon number 6. So that is carbon number 6. So I know I could number that guy up there as carbon number 6. And now I have a way to sort of number all the rest of the carbons. I'm going to come down to the ring, and this is going to be carbon number 5. And we're going to actually go counterclockwise in this case. This will be carbon number 4, carbon number, if I could count right, 3, 2, and 1. First off, any questions so far on that? So take your structure, drop it on its side. Go from really carbon number 5 or the last carbon to the carbon-oxygen double bond. Count how many oxygen carbons there are. In this case, we had 5, so we do our 5. If we counted and we only had 4, we would draw the other ring to start with. The last achiral guy at the very bottom should go up there, up on top. And now we could counterclockwise. So now we're ready really just to kind of complete the picture. We definitely will skip carbon number 5 because carbon number 5 and really carbon number 1 there is what comes together to make that ring come together, and that's going to kind of be this part of it. So this is kind of our carbon number 5 and 1 kind of coming together over there on this side to kind of close up the ring. So if we skip carbon number 5, which it might be hard to see as I kind of highlighted over the numbers there, so I'll just put them over underneath. I'm going to go to carbon number 4, and at carbon number 4, I could clearly see my OH group is down, right? So I'm going to put an OH group going down at carbon number 4. At carbon number 3, I could clearly see my OH group is up. So we're going to go up with a OH group at carbon number 3. Carbon number 2, OH group is down. So we'll go OH on the bottom. By the way, what is on the other side of that line? On the other side of the line is hydrogen. Yeah. And usually they're not included in these pictures. Otherwise, it gets really kind of cramped and crowded with a lot of things. But there is the hydrogen on the other side of that line where we put the OH on each of those. But again, a lot of times we don't include it because it just gets really crowded with the hydrogens. Now that leaves us carbon number 1. And carbon number 1 depends on what anomer you are asked to draw. Either the alpha or the beta anomer. So either the alpha or the beta anomer. Well, alpha beta market, supermarket. Anyone? No? You remember? I can still use that. I remember. I feel like some semester I'm going to say that nobody's going to know what I'm talking about. It was a supermarket years ago, alpha beta. All right. I think they became food for less at the end, I think, but they were alpha beta was a supermarket. So alpha in this case means that we're going to put the last OH group down. And beta should mean it should go up, that last OH group there. So in this case, if we put the last OH group, which would go right here, and we did it down, that would be our alpha. And if you redrew it exactly the same here, I'll go that. And we'll do that. We'll do that. We'll do that. And we'll do that. This would be our beta. And you'll usually be asked to draw one or the other, either draw the alpha or the beta. And that's sort of how you know where to kind of put that last OH group there. Any questions on that there? How do you determine where this guy goes? Is that what you're asking? Or
So it's not six. Not four.
yeah, it's really the result of this is where really your hemiacetal comes from. So you got your like carbon, you got your OH group, you have your hydrogen that's there, and this is like that oxygen carbon group happening, and that's the hemiacetal part of it where it comes together. But to answer your question, the combination of kind of 1 and 5 coming together, the one of those OHs kind of on 5 gets incorporated, the oxygen kind of gets incorporated into the ring, and then you will be told or to draw either one or the other, and that's how you kind of know should you do up or down based on whichever one you're drawing. So if you're drawing the alpha anomer, sometimes referred to, you should go down with the last one. Beta, you should put that last one up. It's kind of like, for example, we'll talk about going from like this back to the original kind of thing. You'll be told like, hey, it's like D or L, and that's how you'll know where to put that last OH on the 5. If you take it out of the ring, kind of back to the straight structure, and then kind of you'll have that information given to you to go the other way. Other questions? All right, why don't you try one here to finish up on? Let's do. Let's just try this one here to finish up. Let's try this. Dun, dun, dun. All right, why don't you draw? Let's go beta. Draw the beta anomer of this guy. See what you come up. Okay, let's take a look since we're kind of getting to the end here, just to take a look at one more here. Again, we're gonna kind of number our carbons. So that'd be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Again, if you kind of drop it on its side to the right, we will end up with something that looks like this. I got 1, 2, 3, 4, 5, and like this guy over here. This would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Once again, as we talked about, if you kind of drop it, everybody to the right goes down, which if you don't want to redraw it, you could just remember that as well, right? Right down, left up. And that would mean that as I drop that down, I'm going to have an OH here, an OH here. Some bad starting on my part there. OH there, and that's going to be actually be an H there. That's the first one. It's like an OH, but without it. There we go. All right, so we're going to end up with an H there, an OH here, an H, and an H. And again, if you want to redraw it, it helps you, you could do so. If not, you could actually just leave it standing and just remember left and right, up and down. Here again, we're going to go from our last chirocarbon, which is right here. It is going to attack always where the carbon-oxygen double bond is. So not always the first one, but really where that is. Again, at this point, you could count up how many carbons should be involved in your ring. That's 1 carbon, 2 carbons, 3 carbons, and 4 carbons. So we're actually going to draw not the one we just drew. We're going to draw the smaller 4 carbon ring like so. Yeah, so we're gonna need this guy here. And again, that's helpful to determine which one of the two you should draw. We know for sure to the left of that, that's going to be our CH2OH in this case, which is this guy, number 6. Yeah, so that's going to be number 6 in this case. We can then number backwards. That's going to be number 5. That's going to be number 4. That's going to be number 3. That's going to be number 2. And where's carbon number 1? Well, it is not part of the ring. It's actually off of the ring, as we can see here, right? So it depends on where it's going to end up as to alpha or beta, obviously, but that is why we are drawing the 4-member ring versus the 5. We can now skip number 5 where the ring comes together. We'll go to 4 and we see our OH group is down. So we'll go down with the OH group. We go to number 3 and our OH group is up. So we'll go up with that guy. And now we wanted to draw beta, which means my last OH should go up. So my last OH should go up. And now what's on the other side of this line? It is that last CH2OH. That is carbon number 1, which is off of the ring. Yeah. So beta would mean, again, my OH group is going to go up. And that leaves where our other carbon is, which is off of the ring, obviously off of the ring on that point. Obviously, the alpha would be exactly the same, except the last side there just flips. Yeah. This carbon group would go to the top. The OH would go to the bottom. Questions on that there? Are we going to lay it up?